The primary bottleneck in modern AI software engineering is secure tool integration. Connecting an AI application to a file system, secure database, and external REST APIs requires building distinct, specialized middleware for each source. Every new AI model multiplied by every new data source yields an exponential volume of custom integration work. This is the N by M problem. Because of this reliance on hard-coded middleware, updating a single tool schema often forces developers to redeploy their entire application. Traditional REST and GraphQL integration patterns are structurally incapable of supporting scaling, autonomous AI workflows. The Model Context Protocol, or MCP, is an open standard designed as the connective tissue for AI-native infrastructure. It introduces a standardized interface layer that eliminates the need for custom glue code between models and data sources. This diagram shows a hub-and-spoke network. The central standard interface layer moves tool definition out of the core application loop. Tool execution no longer happens in the main application. It is offloaded into specialized servers, keeping execution processes isolated from the core AI node. Because the protocol is transport agnostic, this communication happens regardless of the underlying network protocols in use. AI integration shifts from a bespoke scripting task into a predictable systems engineering pattern. The functionality of the standard relies on a strict architectural decoupling. The MCP server on the right has one role: to define and expose capabilities. It functions as an isolated container, capabilities dormant until requested. On the left, the MCP client discovers, accesses, and routes them. The client queries the server to find available tools, sends structured requests to execute them, and parses the resulting responses. Finally, the client takes the executed results and routes them back into the AI model's context window. By separating discovery from execution, AI agents can learn and use new tools on the fly without requiring core system updates. MCP categorizes all capabilities into 3 primitives based on which part of the system maintains control. This table details the taxonomy. Column 1 highlights tools. Tools are model-controlled mechanisms. When a model actively edits a document or changes state within an external cloud service, it is executing a tool. Column 2 details the second primitive, resources. Resources are application-controlled. The model cannot take action on them or change their state. They are used by the application to expose read-only context, handling specific MIME types like raw text and JSON data. Developers configure direct resources with static URIs, or templated resources that use dynamic parameters to fetch data. Column 3 outlines the final primitive, prompts. Prompts are user-controlled mechanisms. They act as pre-crafted instruction templates, standardizing how users execute repetitive workflows. You use a tool for a model-driven action, a resource for application-driven data access, and a prompt for user-driven instructions. The architectural rule of thumb is to never build a model-controlled tool to read static data if you can expose it as an application-controlled resource. Developers construct these servers using the official Python SDK. Historically, connecting models to external functions required manually writing and validating exhaustive JSON schemas. The SDK abstracts away manual schema generation. Native Python decorators define capabilities. The MCP.tool decorator sits directly above the function definition. Standard Python type hints and docstrings allow the SDK to automatically infer the tool's behavior. The SDK compiles those field descriptions into the standardized payload the MCP client discovers. Developers then use a browser-based interface, the MCP Server Inspector, to test and debug their implementation locally. Hundreds of lines of fragile JSON boilerplate are replaced by a few lines of declarative code, accelerating secure deployment. Operating at an enterprise scale, these primitives enable complex, modular system architectures. This architecture represents a wise autonomous organization, where a central agent is surrounded by specialized MCP server nodes for private knowledge, local compute, and third-party APIs. The agent uses a single standardized MCP client to pull data from all these disparate environments concurrently. Private organizational data is bridged with local computation resources without the need for custom one-off pipelines. Because access is modular, each specialized AI agent only receives the precise MCP servers and primitives required for its role. The N by M integration bottleneck is neutralized by a single uniform standard. The Model Context Protocol provides the structural foundation required to build and scale autonomous, agentic business infrastructure.